Like I said, good morning everybody, and it's Webinar Wednesday. I'm Adele Kroch from Food Focus, and it gives me great pleasure to host another amazing informative webinar with the Dairy Standard Agency. This, can you believe it, is session number 8. Jacqueline, you and your team are really doing a wonderful value towards the industry with all the amazing topics that you have covered through this program. And yes, it's September, guys, can you believe it? And like they say, spring has sprung, and therefore the topic today, it's time to clean and it's time to spring clean during this time within the industry. So I am really fortunate to have two gentlemen with us today that will help us to understand what it means to have a credible supplier when it comes to cleaning and cleaning chemicals. They are also going to look at clarifying some definitions of sanitation, and then they will discuss some technological aspects of various cleaning and sanitation regimes and their impact on both the effectiveness and the efficiency of cleaning. They will also look at clarifying color coding standards for both equipment and chemistry. It gives me great pleasure now to introduce to you our speakers for today. Gentlemen, if you can please put your cameras on so that the audience can see that you guys are there and present. So Jeff and John, thank you, Jeff. John, if you can put your camera on, I will appreciate that as well. Okay, John will probably come back just now. He was here recently when we introduced everybody before we started, but let me go on. Okay, so Jeff is from Nutrichem, and Jeff Bayman joined Nutrichem in October. There you go, John, welcome. In October 2019 as the National Sales Director. He's actively selling specialty chemicals within the food and beverage industry since 1990 and focused on providing the best practices and hygiene outcomes for all the customers. John, Jeff, we can't wait to hear what you're going to share with us, but what I'm going to do is I also want to introduce John. Well, John has 50 years of experience in the food and beverage industry and hygiene, with expert knowledge in cleaning chemistry applications, CIP engineering, and microbiological RCA. He has worked for a variety of companies, most with leadership positions, dealing with the global leaders in food and beverage production, and has worked in most parts of the world and lived in North America, Europe, Asia, and Australia. Seems like you've been all over, John. How privileged are you? He has fulfilled several roles from business sector director, application specialist to director of engineering. Spent 5 years in developing and executing a skills development program for all customers facing personnel and challenging tasks with around 3,000 mature students, 25 languages and locations from Mongolia to Chile. Recently, he became interested in biofuels technology based on fuels from crop and legal substrates, and led a global cross-functional team developing solutions, delivering process yield and productivity improvement. He retired from mainstream activities in 2014, and now, how awesome is that, runs his own consulting company, Engineered Hygiene Solutions Pty Limited. Wow, guys, we are so privileged having you both to present this very interesting topic to us today. So without further ado, Jeff, I am handing over to you and looking forward to your presentation.
Thank you, Adele. Hi, John. Hi, everybody out there. Thank you for joining us today. I hope today's session will be informative and somewhat of value to you all. One moment, I'm just waiting for the slides to activate. All right, so we're going to be talking about effective cleaning and disinfection in the dairy industry. along with how to extract maximum value from your chemical supplier. The value add role of the chemical supplier in the dairy industry. John and myself will be sharing learnings from years of collaborative workplace knowledge gained to extract maximum value from your chemical supplier while we clean and disinfect a dairy. We're going to be talking about our Hygiene Partner Program, which for the most part makes a massive difference in terms of how we interact and engage with our customers. We'll be focused on best practice, cleaning and disinfection within dairy processing environments. And as always, we'll always be result focused on the outcomes required by our customers. Importance of being a 9001 certified manufacturer. Increasing consumer demand for food safety, threat of litigation. We've all been subjected to the salmonella outbreak that existed and all the costs related to that many of our large manufacturers incurred. Food processing facilities required the peace of mind that the risk related to food processing is managed well by your supplier. Your hygiene product should be certified and approved. Suppliers must consistently produce products that will meet customer quality and performance requirements. A QMS system that allows for traceability and accountability should there be any requirement to backtrack any particular issue that may occur within the cleaning and disinfection process. Further, the role of the chemical supplier must be a hygiene partner that can collaborate with a customer to set global benchmarks and strive for continuous improvement. Manage product performance to achieve hygiene chemical outcomes aligned to industry-specific food safety requirements. Continuous improvement culture and an outcome-driven focused on best practice hygiene standards, process-ready surfaces to focus on producing safe food with a good extended shelf life and a low cost to clean. Supply chain management is all important. In today's time, if you have a factory that is a 24/7 operation, we don't want to be in a situation where your plant is standing due to a situation where your products can't be supplied to you. And then overall reporting, monitoring and evaluating all processes to ensure that the standards set are met. Typically, when we engage with a customer, we would establish the current status quo. And if you can see this document on the right-hand side, what it does is allow us to outline all aspects of the hygiene partner relationship, set the criteria with to how one wants to manage that process, establish what the current status quo is, identify the gaps, plan actions to close those gaps, implement the changes, train people to ensure that those changes remain at the standard they should be, and then monitor and evaluate. Apologies. Just going back, this is another document that just allows for project management. It illustrates that all projects that are set are completed by certain due dates between the two entities, both the customer and the supplier. Managing CIP regimes. Our focus is always on an effective CIP regime that is efficient, using customized tools to monitor and evaluate CIP performance. Our in-use cost, all important. Energy and water, all important. Tools that we have as an example would be a tracking template, a new technology that is known as verification in place to allow one to evaluate proof of cleans. This here is a document typically that we would put in place to monitor cleaning and effectiveness of the clean, along with all aspects of CIP parameters. This document can be customized depending on each and every entity that we may be working with to suit your needs and to achieve a common goal as an outcome. Another tool that we have right now is known as smart technology. It allows for verification in place, which is a validation of cleaning protocols and troubleshooting monitoring. And it's designed to give you a proof of clean. John, my colleague, will explain a little bit more about this in detail as he presents to you the technical side of the customer hygiene program. Further to that, the role of the chemical supplier should have technology available that is aligned to global trends, reduces demand on energy and water, allows for optimized CIPs, gives you access to a knowledge pool that is international, application methodology that applies best to your needs, has an environmentally conscious focus, leads the way in sustainable raw material selection, product raw material exclusions such as formaldehyde, and MP9s for bioaccumulation potential risks. In addition, considered product offerings should be sodium-free, aligned for recovered water that could be used for irrigation of farmlands, etc. Biodegradable and digester-safe chemicals, energy and waste management, potentially to harvest rainwater for the production of chemicals, solar energy to reduce your footprint, effluent treatment, reuse of plastic containers where possible, repurposing and recycling of old RBCs, blowpacks, and polycans, things of packaging of that nature. At this point in time, I'm going to be handing over to my colleague all the way from Australia. John, welcome.
Thank you very much, Jeff. Good morning, everybody. My name is John Cornford, and I'll talk about some of the technical aspects of cleaning and disinfection. I'd like to start this off by talking about some definitions. I'll just wait while the link from Australia to South Africa works. Just hold on a moment. I'm having a small problem with the slide management. Okay. Excuse me for one moment while I bring this back under control. Okay. If we start off by talking about some definitions, and we'll start with definitions about cleaning. Cleaning is the complete removal of residues and soil from surfaces using water, detergent, or enzymatic products, leaving them visually clean and so that subsequent disinfection treatment can be effective. You cannot disinfect dirty surfaces. Physically clean, it means visually clean to a satisfactory standard. Dry surfaces and strong light sources make a big difference to seeing what is visually clean. I use 150 watt LED panels instead of torches to look at tanks, and the results are startling as many otherwise unseen imperfections become visible. Chemically clean can be defined in various ways. That there's no detectable soil by chemical analysis, that there's a water break-free surface, meaning that water does not bead on the surface in indicating the presence of residues, or something called the camphor test. The camphor test is a very sensitive test for oily residues, particularly useful when you're validating the cleanliness of newly installed tanks. And the last one is microbiologically clean, which says that any residues are insufficient to infect product contacting the clean surface. And if we move on to a second set of definitions related to disinfection. Disinfectant is a product used for its ability to kill specific microorganisms, meeting specific standards of log reduction under specific conditions. So chemical products falling into this category are highly regulated and covered by a range of standards, including testing under soiled and unsoiled conditions, testing in hard and soft water, etc., etc. Disinfectants are typically used in a two-step process of cleaning followed by disinfection. They're clearly defined and codified around the world and recognized as high-level activity materials. The South African standard for disinfection, SANS 54885, is aligned to the European standard, EN 13697, so there's an alignment of standards. And South Africa further classifies disinfectants according to meeting various standards for killing different microorganisms in different physiological states. The second definition is about sanitizer. Sanitizer is a term associated with disinfection, but it's got vastly different meanings around the world. So in South Africa, I understand it's generally used to describe personal hygiene products such as hand sanitizers. In the US, the EPA defines sanitizers as products which must kill 99.9% of bacteria, or a log-3 kill, on surfaces within 2 hours of exposure, but not viruses. Clearly, such a product is not very useful to us for disinfecting food contact surfaces. The term sanitizer is not codified in the European Union. However, in Australia and Asia, the term sanitizer is synonymous with disinfectant. So you rarely hear the term disinfectant, but you hear the term cleaning and sanitizing almost wherever you go. The last group of products are detergent disinfectants, and the definition for these is a product which is used for a single-step process of cleaning and disinfecting. The disinfecting efficacy depends on the degree and the type of the surface soiling, as dirty surfaces cannot be effectively disinfected. So as the soiling level changes, there may be an issue with the consistency of result. They can be used for interstage cleaning, where there's a rigorous full two-step clean and sanitize later. They're useful on light soil conditions, where the pre-rinse will remove water-soluble soils, and they're somewhat used there. There's a lot of R&D effort into this style of product, and there are clear advantages, obviously, to single-stage cleaning and disinfecting, but some care is necessary. If we move on to definitions about some applications, and talk about firstly CIP. So CIP means cleaning in place, and it's cleaning and disinfecting processing plant interior surfaces without the need to dismantle, including vessels and pipe work and valves and heat exchangers and centrifuges and filler interiors and so on. COP is cleaning out of place, which traditionally involves stripping plant to its component pieces and placing them in a tank of detergent, which is circulated to provide mechanical action. This has been largely superseded by CIP. Disinfectant, soak, and storage tanks still fit into this category, and they're used to disinfect parts after cleaning and store them in process-ready condition until they're next required, and that's still quite common. OPC means open plant cleaning, and it's a process for cleaning and disinfecting exterior surfaces by spray, foam, or manual cleaning. And sometimes the application is done by an operator and sometimes by fixed automatic systems. EFC, the last one, is exterior filler cleaning, and it's a subset of OPC, usually specific to rotary fillers, and it generally involves a fixed jetting system and an automated cleaning program. We talk for a moment about factors influencing cleaning, and the graphic here shows you something that's called Sinner's circle, and it shows that the four key factors for cleaning are chemical, time, mechanical action, and temperature. Effective cleaning relies on these three energy sources: mechanical energy, chemical energy, and thermal energy, and applying them for a period of time. If we think about mechanical energy being applied in various different ways, the scrubbing action of a brush or cleaning pad in manual cleaning, or the scrubbing action of high velocity turbulent flow conditions in a CIP pipe cleaning, or the scrubbing action of falling liquid films in a low pressure vessel cleaning scenario. Chemical energy for cleaning takes many forms depending on the soil matrix and the chemistry applied, and the water condition as well. Amongst others, we consider simple dissolution, where an acidic detergent would dissolve a scale, for instance, saponification of fats and oils, where strongly alkaline products act on something like milk soils, surface tension reduction by wetting agents, allowing cleaning agents to penetrate soils, to emulsify oily soils and to reduce the foaming tendency of foam generating soils, things like proteins. Thermal energy is pretty straightforward. The rule of thumb is that the chemical reaction rates are doubled for every 10 degrees C rise in temperature. However, thermal energy usage and the cost can contribute significantly to the overall cost of cleaning. So this is generally people are tending to reduce temperature, not increase it. Different applications rely on different balances of these energies and on applying them for different times. So if you look at the graphic, it shows you on the left-hand side various different processes, and then something about the energy sources, and then it shows you with some ticks something about the amount applied and the time they're applied for. If we talk for a moment about chemical supply instructions, there are many instructions required of suppliers. So product composition and efficacy instructions, safe storage and usage of product instructions, the collaboration and development of standard operating procedures is one of the most important things. So all cleaning and disinfecting processes must be covered by detailed SOPs, standard operating procedures. And they should be developed by the user and the supplier, because the supplier is the guy that knows about the chemistry he wants to apply and the best conditions for doing it. So these should cover the object being cleaned, the frequency of cleaning, and the maximum period from empty to clean. So yeah, you don't want tanks to sit empty and allow soils to dry out. They become much more difficult to clean. So it needs to be specified. The frequency of disinfection, including after periods of plant inactivity. So if you clean and disinfect a tank and it's not used for 72 hours, should you be disinfecting it again before using it? There should be a standard. Requirements in preparation for cleaning, detailed program cleaning, including for each step, the temperatures, the times, the chemical products and concentrations, including sampling and testing regimes, flow rates if they're applicable, pressures if they're applicable, rinse step terminators, which could be something like pH or colorimetric tests, and then post-cleaning requirements. It might be about visual inspection, final rinse water analysis, whatever it might be, but there's some things that need to be done after the cleaning to validate it. And lastly, the completion of cleaning records and the logging of any unusual events. We'll talk for a minute about CIP management and efficiency and effectiveness of cleaning. So CIP can be classified as effective and efficient. Effective means that after CIP operations, the plant is clean, it meets the required microbiological standards, and it's process ready. Efficient means that the plant is clean and process ready at a reasonable cost, including utilities such as water, heat energy, effluent chemistry, and production downtime. The key factors that impact on effective CIP are the correct programs, usually combining pre-rinse, detergent wash, post-rinse, disinfection, and a final rinse step if that's applicable. The correct flow rates and pressures for the plant items being cleaned, necessary to create the correct amount of mechanical action. This is absolutely critical and is often overlooked and missed. The flow rates for pipes are relative to the pipe diameter, and creating flow velocities in excess of 1.5 meters per second, probably with a maximum of maybe 3. For vessels with low pressure spray devices like spray balls, the flow rates relative to the vessel's circumference and to some extent to its height and the soil load. The correct detergent chemistry is important, and the correct selection of disinfectant for the application. The correct temperature for optimum cleaning, and the correct program times for detergent action, effective rinsing and disinfection. So those are the things for effective CIP. If we talk about efficient CIP for a moment, this is about minimizing the losses of chemistry, water, and thermal energy. And in a typical world, minimizing these losses reduces CIP time, and so it also reduces production downtime. Assuming that hot CIP temperatures have been optimized, most losses occur during CIP phase changes. So this is when you're changing, say, from rinse water to detergent or detergent back to rinse water, etc. Creating specific steps in the CIP program to manage these interfaces is critical. The objective is to create program steps that minimize the opportunity for different phases to mix by managing the interfaces into pipes where they're confined and not in vessels. These steps are employed each time there's a phase change, and they're special to each CIP circuit, each CIP object. The efficiency is measured by comparing the detergent lost during the CIP process to the detergent quantity in the CIP circuit being cleaned, because detergent's easy to measure. So we find an easy way to do it. Efficient CIP would be characterized by line CIP losses of, say, 6 to 10% of circuit volume. So that means that if you had a CIP circuit where the volume was 1,000 liters, say, that'd be a medium-sized tank with its pipe work. And if you were cleaning this 1,000-liter circuit at 2%, then you would expect on a line to use 1.2 to 2 liters of concentrate detergent. Vessels are much more difficult, and you have greater losses because you can imagine the rinsing process is not so well confined. And you'd expect to lose 15 to 20% of circuit volume. So in a 1,000-liter circuit at 2%, you'd expect 3 to 4 liters of concentrate. Efficient CIP interfaces have very characteristic conductivity signatures, making them easy to monitor. So if you look at the graphic on this page, the part include, no, we're graphing various variables in the CIP process, and inside the white box there, there's a red vertical line, then a green line, and then a red vertical line again. This is the conductivity, and you can see that here it's very efficient. The conductivity is going from very low to very high very, very quickly. There's little or no mixing going on, and the same when the conductivity comes back down again when the rinse starts. If we move on and think about or talk about what happens when CIP all goes wrong. So for ineffective CIP, so this is, I've done the CIP, but things are still dirty. What are the actions? The actions are to check the CIP program operation with the original protocol. Has something changed? Did somebody bypass a step? What the hell's going on? Need to check that the operation of the CIP object for things like blockages, leaks, and malfunctions. So are the spray balls still in place? Are the spray balls blocked? Whatever it might be, are the valves opening correctly? Need to check for changes in manufacturing protocol impacting on soils. So has somebody changed the way that processing is done, or the type of product that maybe flows down the pipes or flows through the tanks? It's changed, it's making everything difficult. You need to check the times, temperatures, flow rates, concentrations, and so on. Check the instrumentation. I mean, with the best will in the world, instrumentation is calibrated regularly, but you very often see problems with instrumentation that mean that the feedback values to CIP are incorrect and the CIP performs incorrectly. When you've done all of that, you usually have enough data to be able to resolve the issue. The second one is about inefficient CIP actions. So if the CIP is much too expensive, then okay, what's going on? And again, firstly, you check the program operation with the original protocol, check the interface management steps, and any changes to the object configuration. So the interface management steps are very critical to keeping the interfaces in pipes and not in tanks. And if the pipe work has changed, then it will then the whole thing will be wrong. Check water volumes, chemical concentration and usage, energy usage against the original protocol. Check the chemical recovery efficiency. Remember the 6% for pipes and the 15% odd for vessels. Check the rinse endpoints and use the data to resolve the issue. If we talk for a moment about cleaning and disinfection validation, we talk about it first for CIP. The traditional validation methods are systems integrated into the CIP control system, where it's recording and comparing some key CIP parameters with a benchmark. And the key parameters would usually be conductivity, flow rate, and temperature. And if the values drift far enough away from the benchmark, then it'll throw an alarm up and maybe stop the process or wait for somebody to take some action. The second one is visual inspection. This is a little problematic as it breaks the post-disinfection security, but it's satisfactory if it's performed before the final disinfection process. After all, the tank should be clean, or the vessel should be clean, or the lines should be clean before disinfection. Microbiological swabbing and ATP testing, and sampling of final rinsings from CIP cleans for microbiological testing if there's a final rinse. There are new colorimetric detergent technologies based on oxidation reduction chemistry with a color change from soil to clean during CIP, and these are becoming very useful. When we talk about exterior cleaning and validation, it's traditional all the way. So traditional visual inspection techniques with strong light sources, traditional swabbing techniques, but now the use of dye technologies to clarify shadow areas where automatic cleaning systems aren't reaching, and the general cleanliness of automatically cleaned items on things like fillers. Try that again. Let's talk for a moment about the verification of rinse water, and we'll talk first of all about usage. So every rinsing step must have a defined terminator that's not based on time. Time doesn't rinse anything. It may be applied for a time value or as a volume, but it should be based on a measurement critical to that process. So rinsing occurs as pre-rinsing, which is prior to cleaning as a gross soil removal step. Post-rinsing after detergent steps to remove soil and detergent residues. And final rinsing generally after disinfection steps if it's done. Pre-rinsing may use recovered water, and its endpoint is usually managed on time or volume, but it's based on measuring the level of soil in the outgoing pre-rinse water. You want to rinse away all the soil that you can. Good measures would be turbidity or color, or bricks for sugary soils, or pH for acidic soils. Post-rinsing is typically removing acid and alkaline detergent residues, and it's usually managed on conductivity. Conductivity is a poor indicator of concentration at low levels. It's very good at operating concentrations, but very bad for rinsing. And managing on time or volume based on pH is much more effective. And the graphic on the left-hand side shows a post-alkali rinsing process, and it shows you the conductivity in blue and the pH in red over time. And you can see that the conductivity has gone to close to 0, but the pH is still something up around 11.5, which is definitely not a satisfactory endpoint. Final rinsing specification is critical, as residues will contact product. And where final rinsing is required, it's often managed on conductivity, but it's better managed on pH or residual disinfectant concentration. Typically levels of less than 1% of disinfectant operating concentration are considered to be satisfactory. If we move on and talk about verification of rinse water microbiology, when the pages catch up with me, here we go. Microbiological quality of rinse water is very important. So pre-rinses are generally performed with recovered water, and if excessive volumes of recovered water, recovery CIP water are brought back, the recovery rinse tank can become very infected and become an infection risk to the process. So CIP programs should be organized to recover enough water for the pre-rinsing process and no more. Post-detergent rinses are performed with potable water, and despite effective water treatment programs, it's not uncommon for the potable water distribution system and the CIP freshwater tanks to develop biofilms, causing a variety of infections. Regular testing and cleaning of CIP rinse recovery water tanks and CIP freshwater water tanks is indicated. A frequency of every 6 months would not be unusual. In a situation where potable water rinsing occurs after a disinfecting step, collecting a sample of the rinse water at the end of the rinsing process and evaluating it microbiologically will provide a powerful indication of the plant item hygiene level after CIP. And the blank collected from the CIP fresh water tank at the same time is indicated to make sure that you're not disinfecting with poor microbiology water. Talk a little bit about the equipment to use. Run on a little. Excuse me while we go back. There's a bit of a time delay between Australia and South Africa. And one more, I think. So if we assume that there are four key cleaning methods: manual cleaning, cleaning out of place, cleaning in place, and open plant cleaning. The equipment for manual cleaning is typically brushes, squeegees, and scourers of synthetic materials, and they should be color-coded by usage area, and we'll discuss that a little later. They must be disinfected regularly and carefully stored to prevent them becoming an infection source. COP, cleaning out of place, traditional COP is about placing stripped parts down into a tank and recirculating it. And this is still done. There's not a lot of it around, but the tanks have mainly been repurposed for disinfection out of place, where things like hoses and parts are left to soak in a bath of disinfectant until the next required. This is standard practice in many plants, and the key issues are the management of disinfection concentration over time by sampling and correcting the concentration, and the regular dump and replenishment frequency for disinfection disinfectant solution in the tank. If we move and think about CIP and OPC, for CIP there are two traditional equipment styles, single-use CIP and recovery CIP. Assuming the correct parameters of flow, pressure, temperature, chemical concentration, and time, both will clean effectively. Both have advantages: a single-use system, low capital costs, and as there are no recovery tanks, and the associated pipework valves and instrumentation program that goes with those recovery tanks. They have a much smaller footprint, again, because they don't have any recovery tanks. They use fresh chemical for each clean, which is advantageous in some high-risk scenarios. The downsides of single use are firstly the operating costs, because there's no recovery of anything, of water, energy, chemical, whatever. And secondly, program times are longer. Recovery systems have a high capital cost and require more space because of their recovery tanks, but the running costs are far lower. And as they recover water chemistry and thermal energy, program times are shorter as well, as the chemistry and temperature are ready to run. Perhaps the best systems are the hybrid systems that recover and store water chemistry and thermal energy for reuse, but only take enough solution into the local circuit to clean the plant item. Alternatively, they can make up fresh solutions for critical tanks. If we just talk about OPC briefly, normally this is fairly simple Venturi feed units. We move on and talk about color coding, and we'll talk about color coding of what we refer to as utensils. So this is brushes and so on. Much of the cleaning and disinfection in dairies is automated, ensuring the correct parameters for effective cleaning and minimizing cross-contamination risks. Exterior cleaning is generally a manual process, and it relies on the operator to select the correct cleaning chemicals and applicators. Selecting the wrong cleaning chemistry can result in poor cleaning and product risk or corrosion risk. Selection of the wrong applicators can result in cross-infection. In the worst case, for example, using the same brushes for cleaning cauldron drains to process surfaces. Color coding of chemicals and applicators with appropriate training helps to mitigate the risks. If we just talk about something about maintaining the integrity of process-based hygiene zones, every year Listeria and Salmonella cross-contamination incidences are significantly responsible for food illness and outbreaks of food recalls globally. Color coding of utensils specific to zones and contamination risk can reduce the operator error in utensil selection. And here's a graphic that talks a little bit about cleaning drains and cleaning outside of processing tanks, and how they have to be separate. One is black and one is blue. You need to communicate using a color coding plan that talks about what color and which process and some comments about it. And then you need to communicate the plan in a very simple way. And lastly, we'll just talk for a moment about color coding chemicals. So color coding for different chemical types is important, as the product names may not have any relevance to the product chemistry, and the detailed information on the label is rarely read by operators. So color coding, if the color coding scheme is trained, then it provides a quick visual indication of the type of product and an indication of the hazardous nature of the product if it is. The most hazardous nature of the product will dictate the color code, and the chemical storage areas should be well lit, ventilated, and clearly demarcated. All acidic products should be isolated from chlorinated products and alkaline and neutral products. An oxidizing agent should be stored away from organic materials such as wood and cardboard. And that is the end of my presentation. I hand back to Jeff.
Thank you, John. Very insightful. I'm sure there's a lot for everybody to take home from that. Just waiting to get control of the slides.
Jeff, I'm sure if it is, what I'll do is I'll move it on my side for you.
Thank you, Adele. Right, in closing, all of what is available as a supplier to a particular customer is very much holistically encompassing. And without committed people, both from the supplier's perspective and within the client base, we've been unable to provide the best outcomes regarding CIP outcomes, cleaning, sanitation, and obviously the all-important in-cost chemical usage. A supplier should be able to give you a 24/7 on-call troubleshooting outcome, supply a product on time, and drive standards with industry application knowledge through training, good monitoring programs, and quality record keeping, with a constant involvement of communication with the client, with all role players, and always to keep a health and safety consciousness awareness with regards to it. We'd like to thank all of you who joined us. We appreciate your time and really hope that you enjoyed the webinar. Thank you, Adele.
Yes, thank you, everybody. Well, I must say, it seems like you two gentlemen has covered this topic very, very well, because currently I cannot see any questions from the audience, from the attendees. So attendees, are you still there? Did you listen? Do you have any specific questions for us that you would like to ask these two gentlemen? I will give it a few minutes and see if there's any questions that's coming from the floor. If not, I would suggest that if you do have questions, that you then send the questions through to Jacqueline at the DSA, and they will look into it. One thing that I would like to ask is, do you gentlemen often get questions from your clients where your clients struggle with auditors asking them specific questions on the CIP that you are aware of, that you know, the people within the industry often struggle with? Jeff, from your side?
Hi, Adele. Thank you. Questions is an ongoing thing, and we learn every day as we work together with our client base. So yes, there are questions, but most of the time we would apply the knowledge and work together with the client to get the desired outcome.
Okay, I've got here one question from Ashwani, and he's asking, what is the normal drop in the concentration of alkalinity or acidity during CIP?
John Cornford, would you mind answering that?
Yes, can you hear me?
Yes, we can.
Adele? Okay, right. The amount of acidity or alkalinity that's lost during CIP has got very little to do with the soil removal process, and an awful lot to do with the interface management. So most of the reduction in acidity or alkalinity, unless you're talking about pure scale removal with acid, but if you're talking about a general cleaning process, it's almost invariably about the amount of alkalinity or acidity which is mixed up with water during the interfaces, and very little about the almost a negligible amount to do with the cleaning process itself. Okay.
Okay, Ashwani, I hope that answers your question. I would like to ask a question. You say that there's quite a big importance in terms of the color coding of the equipment and all of that. Do you often do the training for your clients in terms of the usage of the different equipment and explaining to them the color coding processes? Jeff, I think that question is towards you.
Adele, yes, all of the time. So critically, when we set up a cleaning regime or a cleaning program, we would be engaging with the client to establish color coding by area, by application. We do a whole lot of visual support to do that in the plant and both within the cleaning manuals. And then the training is ongoing. Our training can be anything from weekly to monthly to 3 monthly, depending on which component of the training we're looking at. So training is a continuous work in progress part of the supplier partner relationship.
Yes. Okay, I can't see any other questions coming from the floor, but I think the audience will agree with me that it is extremely important when it gets to the PRP of cleaning within this, within your manufacturing area, how important it is to make sure that you are utilizing a company that can provide you with the correct information and support. I mean, as you guys saw through this presentation, it's a science on its own, and we need to make sure that the process or the company that you choose to work with gives you the absolute support like we've seen you're supposed to get during this process. Okay, I see I've got one more question. Also again from Ashwani. At what stage color technology verification should be used and how frequently? At what stage? Ashwani, I think if possible, I'm going to try to unmute you so that you can ask the question directly, because I'm not too sure if the way that I'm reading the question makes sense. So let me just quickly find you, and then I'm going to unmute you, and then you can ask the question directly. Let me just see, where are you, Ashwani? At what stage color technology verification should be used and how frequently? Does it make sense, the question, to either you, Jeff, or John?
Adele, yes, it does. I'm going to ask John Watkinson to answer this one for Ashwani.
Hi, can everyone hear me?
Yes, we can, thank you.
Okay, Ashwani, it's a very good question, and you would want to use the color change technology to verify that you have a clean. So it is normally performed post-clean, often pre-disinfection, because as John mentioned on the call, you can't disinfect a surface unless it's clean. But I've known it also to be done post-disinfection, because depending on the technology you're using, certain of the technology can pick up microbial contamination as well. So it can show you whether you've got a good disinfection. That still needs to be validated via your routine microbiological standards, but it could be a very instantaneous check that your disinfection programs worked as well.
Thank you so much, John, for that answer. I'm sure of it, that is clear. It's even clear to me now as well. So if there's no more questions from the floor, I would like to thank everybody that signed in today. And I just want to make you aware that when you go to our website, www.foodfocus.co.za, the recording as well as the presentation that you saw today will be available for download, and you will be able to listen to the recording again as well. And just for your information as well, Food Focus is part of the Food Risk Forum group. And please make sure that you sign in to receive our newsletter to make you aware of topics and webinars and discussions that we've got on our different platforms. I would like to say thank you to Jeff and John for the amazing information that they shared with us. And I would like to wish all of you a very pleasant Wednesday. And yes, until the next time. Thank you very, very much, everybody.
Thank you, Adele.
Thank you, everybody. Thank you.
Thanks, John. Thanks, Jeff.